Okay, I wanted to start talking about acceleration and formulas for it in general, okay, instead of just a uniform circular motion or linear motion, more general motion. To start that, let's go ahead and remind you here of what we showed in some previous videos here, that linear motion can be written this way. I've got the acceleration as a function of time being what? The second rate of change of arc length or distance traveled with respect to time times what? The unit tangent vector, okay, in direction of increasing s and t, presumably, okay? So in this case, t hat is constant, right? Okay, and we're going to see here, this is a tangent vector to the motion. This is actually the direction of the linear motion. Later on here, t is not going to be constant, but for linear motion, we know that it is. Uniform circular motion, we showed this in the last one. We could write it this way. For uniform circular motion, you've got constant speed, right? Acceleration as a function of time turned out to be what? The speed squared, okay? Notice there's no bar on that. That would make no sense anyways. But v is ds over dt, right? The rate of change of arc length with respect to time. So it's speed squared divided by what? The radius of motion, right? The radius of the circle of motion. And n hat is what? The principal unit normal. That happens to be pointed directly inwards towards the what? The center. That's got a hat on it. Remember, that's a unit vector. Anyway, so we've seen both of these already, and I just want to remind those, okay? Before I do anything else, let me throw in one last thing here involving the meaning of curvature, okay? Okay, this is another idea. You guys should know what the curvature means anyways. This is kappa again, not k. It's a Greek k. Kappa equals the magnitude of what? D t hat over ds, right? All right, t hat on a general curve is going to be pointing in different directions, right? T hat is just what? The direction which the particle is moving along the curve, right? That's direction. That's a direction vector. And that's the rate of change of t hat with respect to arc length. Okay, so how... Now, let's mention here that since that's t hat is pointing the direction of motion of the particle along the curve, the actual value of t hat, I should say the magnitude of t hat never changes, right? This is purely showing motion. So if there's any change of t hat with respect to arc length moving along the curve, if there's any change here, it's going to be just a change in direction, isn't it? There's not going to be any change of magnitude of t hat because they're always unit vectors. Okay, so this is showing how quickly, basically, the object is turning. Okay, the little particle moving along the curve. Or if you want to, think of how quickly the curve itself is changing. Okay, remember this was our definition here. Okay, and then we also had a definition in a previous video for the principal unit normal. dt over ds itself, not the magnitude, but dt over ds was what? Kappa times n hat, and that was our principal unit normal. So these are definitions here. Okay, now I'm going to come over here just to help with another slight definition of curvature, an idea of what's going on here. I'm going to imagine this as being a smooth curve. Okay, do you see here? It doesn't look very smooth here, but there it is. It's supposed to be smooth, so I'm imagining a particle moving along this curve, maybe. Think of it this way, moving along like that. Okay. And at each point on the curve, there's going to be what? The unit tangent vector. Okay. Here, I've got the point P, and over here I've got another point Q. Okay. Since it's moving this way, I will assume that delta S is positive here. If it was moving in the opposite direction, delta S would be negative here. But we'll just assume delta S is positive here in my drawing. Anyway, so I've got this parameterized in terms of S from some starting point on the curve, wherever that starting point might have been. So I've got t hat of S here at point P, t hat of S plus delta S here at Q, okay? So the length of the curve from P to Q here is actually delta S, and I've got that labeled there. Okay, now here's something I'm going to do here. This delta phi, I shouldn't say delta phi, I have it written as d phi, this angle right here, see this guy right here? Okay, I'm going to imagine that that's the unsigned angle. Okay, so this is always going to be greater than or equal to 0. I'm going to imagine that's the unsigned angle between the two vectors. Okay, so imagine I take what? These are free vectors now. I could imagine moving them. Okay, and moving them so that they what? They have the same initial point, and then there would be an angle I'm calling d phi between those two vectors. And again, they're unsigned. These are unit vectors. These are d phi, I want to emphasize, is unsigned, so it's greater than or equal to 0. Okay? All right. Now you see pretty clearly here that d phi goes to 0 as delta s goes to 0, right? Okay? Now when I talk about angles between vectors, I usually stay away from using the cross product, right? Because the cross product has the unfortunate consequence that, you use the sine inverse when you're trying to find the angle between two vectors. You would have a problem because, an angle between two vectors is between 0 and pi. Well, the sine can't differentiate between the sine of phi and the sine of pi minus phi, right? Okay? So that's why we generally don't use the sine to find the angle between vectors. We use instead what? The cosine and the dot product. But anyways, I'm going to make an exception here because I know d phi is getting really small as delta s is going to 0. Anyways, just consider the following. The magnitude of the cross product of these two unit tangent vectors. Okay, you remember the cross product? The magnitude of the cross product is what? The product of the magnitude of the two vectors times the sine of the angle between them. Okay? Now, here, the sine of d phi times 1 is the result we're getting, right? Why? Because these are both unit vectors. So you can see this just boils down to the sine. It almost looks like sinh. That's supposed to be sine of d phi. Okay? Now, let's do something real quick here. Suppose I did this. Do you guys remember the cross product of any vector with itself is 0? Yeah, if I take the cross between any vector and itself is 0. So if I was to play a little trick here, imagine this difference crossed with t hat of s. Well, the t hat of s would cross on the t hat of s, giving the 0 vector, right? So that wouldn't make any difference at all. This is actually equal to what? The original up here. So you see this equal sign right here is indeed valid. Okay? Then I'm going to do what? I'm going to divide this quantity by delta s, and I'm going to put delta s outside the parentheses. Again, I'm assuming delta s is greater than 0. I've written there. So you need to put absolute values around delta s. Anyways, you remember that what? If this was supposed to be equal to the sine of d phi, so if I have the sine of d phi and I divide by delta s, I would get what? The magnitude of the cross product of what? Delta t divided by delta s crossed with t. Okay, t hat. All right, so this clearly follows from the equation above. I just divided on both sides by delta s. Okay, now I'm going to play one last little trick here. I'm going to take and divide and multiply on the different factors here by d phi, as you see. These would just cancel out. Okay, and I'm still have this, and then take the limits as delta s approaches 0. What happens to, you remember a fundamental limit in Calc 1 was what? As d phi goes to 0, right? The sine of d phi divided by d phi goes to 1. Remember that? So this thing is going to 1. Why? Because as delta s goes to 0, d phi goes to 0, so that ratio goes to 1. Okay, so we're left with this. This becomes ds here. Okay, I'll write this as instantaneous or differential change, and this same thing here. So we've actually got this. Okay, now what was this? Oh wait, I recognize that guy right there. Remember that? That's kappa times n hat. Oh, okay, so let's come back here. and make that substitution. That's kappa times n hat. So I've got d phi over ds is equal kappa n hat crossed t hat. I can take the kappa out because remember kappa is always greater than or equal to 0. N hat and t hat are both unit vectors and they're orthogonal to each other, so the magnitude of that cross product is the magnitude of the area of the parallelogram formed by the two. This should have a hat on it, and that is 1 because that's actually a square, so that's kappa. So what we can ultimately say is curvature is also this. It's the instantaneous rate of the angle between unit tangent vectors with respect to arc length. This is another interpretation of kappa, the curvature. Once again, it still gets the idea of what? How quickly the unit tangent vectors are turning. The units of kappa are therefore what, though? Radians over length. But remember, radians are what? They really don't have any measure at all. Radians are, in fact, unitless. So it's actually 1 over length. Okay? So curvature is measured in like reciprocal meters. Meters to the -1 power. Or centimeters to the -1 power, depending on the length you use. Okay? Alrighty, so there you go. General acceleration. Let's finally get away from kappa and get to my main point, which is general acceleration. I have position vector of a point, okay, of a particle moving along a certain curve as a function of time, so t is time t. The velocity is the instantaneous rate of position with respect to time. That's ds over t times t hat, right? T hat is simply the direction that the curve is pointing at a particular point. That's t hat. That's a unit tangent vector. ds over dt is what? Velocity, right? Speed. Okay? So we've got that. That's fundamental. That's easy. That always holds. If I differentiate again, I get acceleration, right? Acceleration is the second derivative of r with respect to time, or the first derivative of the velocity with respect to time. So just using the following rules of differentiation, differentiate with respect to t, ds over dt, t hat here. And what are you going to do? Let's use the product rule. That would be ds over dt, the second derivative of s with respect to time, t hat, plus ds over dt, the derivative of t with respect to t of t hat. Okay, so we've got that. All right. Now I'm going to do this. I'm going to play a little trick here again. Okay, here I'm going to use the chain rule. When I go d t hat over d little t, I'll go d t hat over ds, imagining t is a function of s now, times what? ds over dt. Do you see from the chain rule that these two would go directly to that inside the square brackets? These two together. And then I'm still going to have what? A factor ds over dt on the outside here. Okay? What is dt hat over ds though? That is kappa n hat. And then I've got what? A double factor here of ds over dt. So I've really got what? ds over dt squared kappa n hat. Here's my formula for acceleration. Put it all together. Acceleration is the second derivative of arc length with respect to time, t hat, plus kappa ds over dt squared n hat. Okay? ds over dt is really the speed, right? Okay? Some people write it this way. Acceleration is a sub t, t hat, plus a sub n, n hat. These are what? The tangential component of acceleration, or what? The component of normal acceleration or centripetal acceleration. Okay? And then we can actually show you how to compute curvature. I've got a formula for that. We'll expand upon this in a little while, but let's go ahead in another video. Let's go ahead and consider this here. Does this look familiar at all? What does that look like? Go back to the beginning. Ho ho. That's linear acceleration. Okay? Well, that's linear acceleration, right? Or we would so call that tangential acceleration. Okay, that whole term. How about this part? Does that look familiar? It should. This is what we call the normal component or centripetal acceleration. Okay? Oh yeah. Here we are. Oh, uniform circular motion. V squared over R n hat. And we're going to see here why this and this are essentially the same thing. Okay? Alrighty? Obviously, by the way, you can see this easily. Well, V is ds over dt, right? So I've got V squared already. Okay? That is speed. I could put a V there, right? That's kappa V squared n hat. What's kappa, by the way, when you're dealing with a circle? What's kappa? Do you remember? Kappa is the curvature. Do you remember the curvature of a circle was what? The reciprocal of the radius. It's 1 over r. Okay? So you see how it works here? Alrighty. Let's talk about computing some of this stuff here. Okay? Let's come over here. And you can imagine those being v instead of ds over dt as being v squared if you'd rather. Alrighty. Let's go ahead and think about what I would do if I wanted to actually compute kappa from this formula up here. I've got the magnitude of v cross a over the magnitude of v cubed. Okay? And we'll show you why that is. Okay? So I've got that in a box. This is a formula you want to remember, but it should be in the formula sheet I handed out. This is a different way of computing. This is an efficient way of computing the curvature. Okay? Let's come over here. Acceleration is what? Tangential and normal. All right? See, I've written it this way. I'm going to take the cross product on each side. V cross A. So I bring out A sub t is just a scalar, right? So I've got what? V cross t hat plus A sub n, V cross n hat. Okay? Now, I claim V hat, or V, I'm sorry, I said V hat. V bar cross t hat is going to be 0. Why? Because the velocity in a tangent, unit tangent vector, are parallel, right? They're parallel. They only differ because they're just scalar multiples of each other. So their cross product is the 0 vector. This term will disappear here. How about this one? Well, remember the velocity is what? V, the speed, times t hat. And then I'm crossing that with n. Okay? Well, I can certainly factor out the v here. Okay? And then I'm going to take that v on the outside. And what did we say A sub n was? A sub n was actually kappa v squared. Okay? So I'll substitute that in there. That's actually kappa v squared. That's the A sub n there. So I've got what here? Kappa v cubed times t hat cross n hat. And then I'm going to take the magnitude of both sides of this equation. So I've got the magnitude of v cross a is kappa v squared times the magnitude of t hat cross n hat. But t hat and n hat are unit vectors that are orthogonal to each other. So the magnitude of the cross product is 1 because it's the area of the parallelogram formed by the two, which is a what? Unit square. Okay? So this is what? The magnitude of v cross a equals kappa v squared times 1. So that means kappa is what? V cross a divided by the speed cubed. Okay? So that's v cross a in magnitude divided by the magnitude of v cubed. Since v, with no bar, just the v, is the speed, that's the magnitude of the vector v, the velocity. So there's our formula. Okay? All right, I hope you understood that.